Hello everybody and welcome back. Washing machine motors can be easily recovered and often are in good conditions, are powerful, can spin in both directions and can be driven to control their speed with good torque from standstill. You can also squeeze out much power if a good ventilation is provided. But to better exploit all these features, you need to drive this motor with an appropriate controller. We'll see all this and more in today's video. Let's get started. The most used motor in washing machines, particularly the cheapest ones, is the universal motor. It is named after its ability to work both in alternating and direct current. Essentially, the universal motor is a brushed DC motor that have its windings designed to work properly at the grid's frequency and voltage. And the rotor and the stator windings need to be connected in series. This way, when the current flows through the windings, it generates a magnetic field that is always coherent between the stator and the rotor. And this is a simple explanation how it works. Here, this represents the stator's winding or the field, and here this represents the rotor's winding. And we have a wire that goes here, then through the brushes, and the commutator goes here through the rotor's winding, and then back to the stator's winding. And of course, the wiring can be a little bit different, and then they could be connected this way, but it doesn't make any difference because the current will flow in the same direction. And suppose we have an alternating current, suppose we have a positive here, the current will flow through this wire, and then through this wire through the brush and the commutator into the rotor's winding, and then back to the stator's winding, back to the source of power. And because the current flow in this direction and in the rotor flows in this direction, the current will goes in there and back here on the opposite sides of the rotor. Here is generated a magnetic field when the magnetic field has a north here and a south here, while on the stators on the stator we have a north here and a south here. So north and south will repels, north and south will repels, and the rotor is pushed to spin. And here is hopefully more clear. We have suppose we have this is the phase where the positive is here and negative is here, and the current will flows in this direction, and a north and a south, sorry, is generated here and north here, while in the rotor the wires here are positive and negative here, and so and now a north and a south is generated here, and they will repel, generates a mechanical force that will repel the rotor and push the rotor to spin in this direction. And when the polarity are reversed, because we have alternating current, both the field and the rotor will reverse the polarity, and here we have north and south, and again here south and north. So the polarity still repels and pushes the rotor with the mechanical force that spin the rotor in the same direction. So simple like that. And here we have an example of this kind of motor, a small motor, and this is the stator of the same kind of motor. As you can see here, we have the windings of the of the stator that makes the field. And here we have the rotor. As you can see here, internally here, there is the winding that turns solidly with the shaft of the rotor. And this is an actual washing machine motor. As you can see, the motor is made the same way. We have a commutator here, the brushes, and here maybe it's possible to see. Yeah, here inside we can see the winding of the rotor, and here above the winding of the stator, and the connections are the same. Here we have in addition this thing that is the tachometer. That is a simple generator, because these motors are cheap, or designed to be cheap, so we have just a simple winding with a little magnet that spins solidly with the shaft of the rotor, and this will induce a voltage, a current, sorry, on the winding around here, that generates an alternating current. In fact, this kind of tachometer is not a DC tachometer, is a tachometer that generates an alternating current. This one is another washing machine motor. This comes from Bosch washing machine, and it's a little bit different from the other one. It's a little bit larger and heavier, and here we have here we can see the coil of the tachometer. One interesting feature of universal motors is that their speed can be easily controlled by varying the voltage applied to them, but because this voltage is at mains potential and is alternating current, we need a phase angle controller device to vary the voltage, such as a light dimmer. And this is a simple explanation of how the phase angle control works. So here we have the sinusoidal waveform that comes from mains, 50 Hz in Europe, Australia, UK, New Zealand, and most of the world, 60 Hz in North America, and maybe in other parts of America, I don't remember, and half of Japan. And the phase angle control is defined as the point at which, in respect to the phase, the current starts to flow through the circuit. So, for example, here we have 30 degrees, and we have a current just for this little area here and here, and because when there is no current, there is no power. Here the power is 0, and here we have power just in this point, and here we have, for example, 80 degrees, which is almost half power, and under 50 degrees, which is almost full power. And to control the point at which the current can flow, we can use a triac, controlling the triac through the gate with a pulse to the gate. We can control the point at which in respect to the phase under 80, 90, and 0 degrees, and all the in the middle values, we can start conducting the triac, and therefore making the current to flow through the circuit. Of course, this assumes the circuit have a resistive load to make the thing simple and not a reactive, because in the case of a reactive load, the things get a little bit more complex. So to control the angle, we can make things like this. We can generate a ramp that is synchronized with the phase of the mains. So when the phase begins here at under 80 degrees, the ramp starts here and is synchronized with the mains phase. And if we match, if we compare the level of the ramp against a voltage, a reference voltage, for example here say put negative 1 volt, we can control the point at which, when the intersection happens between the control voltage and the ramp, we can control the point at which point a pulse is generated, and the pulse will trigger the track that will enter in conduction and makes the current flow through the circuit by varying therefore the point at which point the current will flow and varying the angle in respect to the phase. So for example here, when we reach negative 2 volt, the point of intersection happens here, and therefore the trigger to the gate of the track happens here, advanced and therefore close to 90 degrees. And so in this way we can control the phase angle at which point the circuit receives current. And this is a crude schematics of a phase angle controller. And here we have the mains that goes to the track and then through the track to the load and back to the mains, and a branch of the mains is used to go to a zero cross detector that detects when the phase starts, and when the voltage goes below a given threshold, a pulse is generated. So the pulse will tell when the phase starts, and through an opto isolator the signal, the pulse, is fed to a ramp generator that therefore will generate a ramp that is in synchronous with the phase of the mains, and the ramp and the generated ramp is fed to a comparator that compares the level of the ramp with the voltage coming from reference control voltage that is used to control the angle we want to have, and the output of the comparator goes to an opto isolator again, that will in turn triggers the track that will turn on and make the current flows through the load. And of course we can omit these two opto isolators, but if we want to separate the high voltage in respect to the very low voltage to have a safe condition here, opto isolators are a good thing. But this is essentially what a dimmer, light dimmer, how a light dimmer works. But to control motors, this is not ideal, because we have no way to control the actual speed of the motor, and this is important because motors, universal motors, have the windings of the field winding that is connected in series with the winding of the rotor, and therefore the current that flows through the rotor will be the same that flows through the winding of the field. But because the current is proportional to the field, and the lower the current, the lower the field, and the speed is depending on the field. As the field decreases, the speed will goes high, and therefore ideally, if the motor has no load, the current could go tendentially towards zero, and the motor spin at a speed that would be out of control, and even it destroy the motor. And this is why these motors have often a fan, because the fan represents a load that increases its load with the increase of the speed. But with a simple dimmer like the one we've seen, we have no way to control the speed, so we need something that help us to control the speed. And this comes with a tachometer that is axially connected to the rotor, and that can be used to control the speed of the motor. But this requires a specific controller, and that is why I've designed a board to control this kind of motor. Let's see it. Power and check for the voltage. Yeah, okay, 12 volts about. This circuit is not meant to just control universal motors, but a far broader spectrum of applications, including oven control, as we will see in a future video. I think this circuit is interesting for those who are new to electronics, as it features some classic circuit building blocks using op-amps. This is a schematic of the whole circuit that is made of several blocks that can be used for even other kind of applications. In fact, here I haven't installed some part of the circuit. Let's have a look at the blocks of the diagram. I will not go into details of the electronics circuits here in this video, but maybe I will do this in a specific series dedicated to hands-on electronics. Let me know in the comments section below what you think about it. And here we have this part. This is the power supply of the board with a little transformer. This provides a dual voltage plus minus 6 volts. This potentiometer is used to control the speed of the motor or the phase angle. And this is the track unit that we receive the pulse and send the synchronous pulses, and will control the actual power phase angle. And this is the main board that have the key blocks you may find in every closed loop controller. And the circuit is formed by various blocks. Here we have the wire bridge that can be used to balance some resistive inputs, an instrumentational amplifier that can be used to amplify sensors, of course the power supply, and a precision rectifier, and a zero cross detector, a frequency to voltage converter, a pulse detector, and of course the control loop that controls the phase angle and the feedback and the current feedback, and all these blocks can be combined together. They are not pre-wired, they can be combined together through jumpers, and of course this can be used for various applications that have in common the fact that we want to control the power through phase angle control. This is a diagram, block diagram of the driver, the motor speed control, and as I've said, the tachometer provides a signal that is an alternating current that is proportional in amplitude and in frequency to the speed of the motor. So we can choose between the amplitude or the frequency to detect the actual speed of the motor. I rather use frequency to get rid of variances between voltages between motors. So I use frequency, and to detect the frequency, the tachometer signal is comes here, and here we have voltage divider and a limiter through these diodes that limit the amplitude of the signal to the rail of that supply the circuit, and a little bit of bias to get rid of possible noises that could generate random frequencies at the output of the circuit of the zero cross detector when the motor is not spinning. So the output of the zero cross detector, that is a frequency that is proportional to the speed of the motor, is fed into the frequency to voltage converter that converts from the frequency into a almost linear voltage. Here we have the speed potentiometer that provides a reference voltage for the speed, and through a buffer comes to this node that therefore is added to the signal, to the feedback signal of the speed. Because the two signals are in opposite signs, the result is an algebraic sum, and the error represents the error of the speed that is amplified by the amplifier, and control the pulses that in turn will control the power that goes to the motor, and therefore the speed of the motor. So the output of the error amplifier goes in fact to the comparator that compares with the ramp generator that generates the ramp in synchronous with the mains. Here we have the triac unit that has a zero cross detector that detects the points where the phase starts from the mains, and through two opto isolators provide the signal of the synchronous input to control the ramp generator, and the ramp is then compared to the level of the error signal, and generates the pulses, the common pulses that will trigger the triac through the opto isolator, the triac that will provide current to the motor. And the error amplifier also has this diode that limits the voltage only to one side, because we control the speed just on one quadrant. We have a unidirectional motor here, and here we have a network that provide a feedback that is used as to make an integral and proportional, a time compensation and a gain compensation to the air amplifier, and this is useful to make it stable and avoid oscillations or overshoot in control of the motor. So let's see if sparks come out. So here we have the board, the track unit with the wires that go all the way down to the motor here. So let's give power. Okay, the motor have this jolt at the beginning because the RAM generator is not yet stabilized, and I have to devise something to prevent this to happen. Give a little bit of speed. As you can see, there is a little bit of instability at low speed. Let's try to, if I try to stop the motor reacts and the speed is maintained, even though there's a little bit of instability at low speed. This is because at low speed the frequency generated by the tachometer fall outside the range of stability. But if I give a little bit more of speed, you can see the speed is much more stable, and if I try to stop the motor reacts smoothly and the speed stay consistent. Well, this is a little bit dangerous to do, but I'm using a paper. If something goes wrong, I release the paper and nothing happens. Okay, let's see more speed. As you can see, the speed can reach very high speed. We are at 5,400 RPM. And if you want to learn more about this instrument, you can watch the video, link in the description. This is the signal read from after the yellow track, after the zero cross detector. It is the frequency that comes from the tachometer, and the pink track is the signal that comes from the RPM counter, that the instrument that I put to read the actual speed of the motor, and that provides an output signal from the photosensor. And so this is a full revolution from here to here. Let's stop so we can read it better. And as you can see, there are 1, 2, 3, 4, 5, 6, 7, 8, because yes, this is a little bit shifted, 8 pulses of the tachometer per revolution. So the tachometer have probably 4 magnets, like a cog. The frequency is 8 times higher than the actual revolution of the motor. 217 hertz of frequency from the tachometer, which corresponds to about 217 1627 RPM. And now I try to load the motor. It's a crude test, but the loss of speed is about 4%, and I had to add a couple of capacitors because to smooth out the oscillation due to the conversion from frequency to voltage, and without this we have the motor behave not very good. What? I forgot to if I try to load the motor, it's just unstable. This is how the motor behaves when the proportional or the integral are not correctly adjusted. Here there is too much integral and too little proportional. So if I reduce the proportional, the stability goes up. Wow. Stability rises. This trimmer is gotta be broken. The motor is much more stable here, but if I try to load it, it responds, but it is not as responsive. So if I try to raise the proportional and then remove a bit of integral, the motor is much more stable and responds quite well. Maybe a little bit of more integral. Yeah, and this is the synchronous pulsar, that the synchronism pulsar that arrives from the triac unit. As you can see here, we have 2 milliseconds per division, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So we have 20 milliseconds, which is a full wave. As you can see, the pulse happens when the mains cross the zero, and it is centered around the zero. This is the pulse that reset and start the ramp and synchronize the ramp with the mains, which is represented here by the pink track. And as you can see, the ramp reaches almost the full phase. Both synchronism and the ramp, and at the output of the ramp, here is the intersection, and this is the output where the pulse is generated, and that triggers the triac. Let's change the speed to increase the angle. As you can see, there's a little bit of change because the motor is not loaded. Now I turn it off completely. Okay, I hope you enjoyed this video. Thanks for watching. See you next time. Bye.